Hey, welcome. Thank you for joining us today for our IBM Quantum Industry webinar. Today's webinar topic is on quantum computing for energy and sustainability. And we are joined today by Dr. Bob Parney, who is the IBM Global Lead for Industry Applications in Quantum Computing for Oil and Gas, Energy and Sustainability. And as part of this role, Bob leads quantum engagements with industry partners and develops technical and business focused use cases in quantum computing. Bob is a thought leader and scientist with over 30 years in oil and gas and technology, and the last 8 he spent in quantum computing. So we are excited to have him here to take us through the work we're doing in this industry. Thanks, Bob. I'll turn it over to you.
Thanks, Jennifer. So welcome. Um, so today I'm going to talk about use cases for business, for enterprise around quantum computing, as it says, for energy and sustainability. And but I will just start with this picture on the right here is one of our quantum computers. And I mean, they are really quite amazing devices. They are usually buried within refrigerators, so you can't see them working. And they have a lot of power. In fairly simple terms, every time we add a quantum bit, we double the power of our quantum computer. And while there are some amazing technology things, I'm going to build towards the business value. And right out of the gate, we are quantum is a technology that is very real, but I think it's fair to say it has not yet outperformed classical compute, but we are knocking on that door. Now, BCG has taken a look at the business value of quantum computing, and they break down the broad algorithmic areas for quantum computing into simulation, which is in general molecular simulation, um, optimization, and machine learning. And they see a little bit over 800 billion in broad industry value across all industries and all use cases. And it will take a lot of hard work by people who are looking for how to leverage the awesome power that quantum computing brings to you with problems that matter. And it is at IBM, we have a very large network of enterprises and academics, government institutions. We have over 250 people in our network. And actually, as I was looking through these slides, it's there's in fact a second page, as you can see. So you'll see people like Exxon and E.ON from the energy industry here, Woodside, but also a wide range of other industries, people like Volkswagen, Virginia Tech. So IBM, we work with everybody, and we really feel the ecosystem is very important to move this technology forward. So what are some use cases? What are some things that a quantum computer can do that is actually of value? So for energy and sustainability, we've explored things such as the development of new fuels like green hydrogen. Excuse me. And so we are looking at how do you simulate molecules in a way that allows you to do something new with them. And so even simple models like hydrogen, how do they combust in an engine? How do you produce green hydrogen in a way that is sustainable and uses a minimum amount of energy? A second area is carbon sequestration and storage. So we have a planet that is warming up. We would uh, we have a number of tools available to us to slow that process. One of those tools is to capture carbon and basically bury it. So quantum computing has a potential role to play in this in understanding the processes and potentially make them more affordable. Optimization can give us a help with a transition to renewable energy sources and changes in grid dynamics. And it's not just a problem of it's simply the power sources such as solar are out of sync with the demand. It's also that the systems are more dynamic as we move away from large um, machine-driven turbines to more dynamic changes like wind farms. We also see opportunities in grid modernization and infrastructure, and we're just starting to explore ways of using quantum machine learning to mitigate the risks of weather-related events. And one of the areas that um, we have seen people exploring from very early on, certainly as early as 2016, is exploring doing the groundwork for improving batteries. So a lot of the early work, things that were published in Nature, were around lithium ions. And while it hasn't changed battery manufacturing yet, um, we see a future industry where new materials are developed for businesses around new batteries, new photovoltaic solar panels, even things like corrosion inhibitors. So there's a lot of potential for materials discovery um, using quantum computing. So what are our broad areas of use cases specific to oil and gas, energy, and sustainability? So we often start with simulating nature, which is essentially simulating quantum systems. So a quantum computer is a quantum mechanical system. It's a physical device. It's not simulating quantum. It is quantum. And so one of the first areas that the problems map very directly are things that are themselves quantum mechanical systems. So this is where chemistry, molecular simulation really comes in. As I mentioned, new battery designs, carbon capture and fuels, but we can also look at things like new catalysts and surfactants. So in oil and gas and in petrochemicals, we may be more interested in how do we lower energy barriers? How do we perhaps produce things with less cost and less emissions? Or how do we understand our subsurface and our reservoir more quickly and develop better ways to produce it? And down the road, we see opportunities in reservoir simulation, and as I mentioned before, photovoltaics and corrosion inhibitors. The second broad area is advanced math and complex data structures, which the easiest way to think of that is AI. So we are looking at things like asset failure prediction. We may look at um, uh, layout and design of wind farms and grids. One of the areas that has been fairly successful, some of the more recent work was on anomaly detection. And this is where pulling from one industry into another becomes very powerful. So the actual work was done on fraud detection within finance, but it's mathematically very similar to any kind of anomaly detection. And so we've just pulled that over to start to look for things like how is likely is a machine to fail, um, and similar things. Another thing we've looked at is commodity price and risk. So one of our partners, Eon, did some outstanding work um, looking for a replacement for Monte Carlo to say, instead of looking at all the potential scenarios by doing multiple simulations, we can find a way to leverage something called amplitude estimation with a quantum computer, and very similar things can be applied to commodity price estimation. Third broad area is search and optimization is exactly as you would think it would be. So grid optimization for using electric vehicles acting as remote storage. We've optimized working crews. We've explored optimizing oil and gas production. There's also work by Exxon on marine vessel routing optimization. We've looked at investment optimization and power grids. So as you can see, there's a broad range of potential applications. And I think the trick is now, as we start building bigger and bigger machines, figuring out which of these areas are going to have the most impact for a business. Now, we've talked about the machines. How big are the machines? So here is our IBM quantum hardware, software, and other layers in the stack for quantum computing. And we've had quantum computers live on the web since 2016. And we started out with 5 to 9 qubits. So the qubits are a quantum bit. And we're now up in the hundreds. I believe our latest one that's live is about 157 qubits. But what we've started to recognize is that it's not so much about the qubits as, and it's partially about the qubits, but it's becoming more and more about the size of circuit you can actually run successfully. And so we have now run over 5,000 gates. And I won't discuss all these other layers. You can go to the IBM website. This is discussed in detail. But where things start to get really interesting, we're at 5,000 gates now. We're starting to get up to maybe 10,000 gates by 2027. But if I zoom in here, we go from 10,000 gates in 27, 15,000 in 28 to 100 million in 2029, and then over a billion in 2033. So this is a pretty exciting time to be in quantum because things like error mitigation and error correction are about to transform the way quantum computers work. So let's talk about those a little bit because the last 18 months have I've been in quantum for 8 years. The last 18 months have been uh, uh, really quite incredible in the amount of change. So if you're not aware, quantum computers, while very powerful, are very sensitive. So it is easy to lose your quantum state. It's easy for errors to occur. Um, and so there's this goal of quantum error correction, where everything is essentially fixed. We use a number of hardware changes, software algorithms to correct for the errors. But one of the first things that we've realized, and this came out about, I'm guessing, 18 months ago, is that before we get to full error correction, we will have error mitigation. And so what that means is we haven't eliminated the errors, but we've corrected them enough to do useful work. Um, the second thing that we've done is improving the hardware. So we have improved with new gate architecture. The devices, the noise levels are improving, the coherency levels, T1 times, all of those things are improving year after year. And we've been pretty aggressive about putting our goals out there, which allows us to say with quite a bit of confidence that 2029, this third step, bringing in full error correction, will be achievable. Now, what does this mean for computing? Are we going to replace classical compute? No, we're not. What we see is a future where there is a combination of CPUs, GPUs for a lot of the classical machine learning tools, and a quantum processing unit that are all interconnected and probably quite often co-located. Um, and we see this combined future of computing. And so we are in this transition. We are starting to use error mitigation now. We're up to 5,000 gates. Um, and by 2029, we'll be transitioning more into full error correction. And so we are in the area we call utility. And right now, I think it's fair to say the state of the art is classical computers are still beating quantum computers. But classical computers cannot simulate the kind of quantum calculations that we're doing on quantum computers. So we've passed the point at which classical can simply do the exact same calculation, but classical may beat us with some kind of heuristic. And then down here, just in case you're wondering how you would actually program a quantum computer, it's really just Python code. So we have a number of layers in our system, but at the end of the day, you don't have to learn a new language. It's really just a library that you import. So let's talk about use cases. One of the very interesting use cases worldwide, I've seen a lot of this in Canada, is carbon sequestration. And the idea of carbon sequestration is you capture carbon at the point of emission. One of the ways that you can do so is you inject a group of chemicals known as amines. This basically allows you to trap it in a liquid form, and you can inject it into the ground. In many ways, this is a well understood process um, in terms of implementing it for food production. However, we are facing a 9 gigaton volume of CO2 that needs to be captured per year and stored between now and the end of the century. This is a massive amount. This is far beyond anything that has ever been done. The second issue is that despite it's a fairly simple industrial process, the underlying attachment pathways, basically how does this really work with amines binding to CO2, is actually very poorly understood. And the biggest problem is that carbon capture is simply not cost effective right now. So, given that a lot of our goals are out to 2050 to 2100, there seems like a really good opportunity for quantum computing to play a role in helping this. But where are we now? Well, in terms of molecular simulation, there was this outstanding work done by IBM and part various partners, including Riken, um, where we modeled some fairly large molecules by using a combination of quantum computing and classical HPC. And we ended up with over 10,000 gates. And it was a breakthrough new process with these very large molecules. But the question is, we want to do this amine injection. If this is the state of the art and we've actually improved even upon this, how close are we to being able to inject these amines? Well, as it turns out, so here are a few, these are the number of qubits required for various uh, chemical reactions related to amines. And the best way to describe it is, well, first of all, let's be very clear, we can't yet do the molecular simulation of the full commercial amine injection. But what we can do is we can just start scratching the surface of that. So we are able to look at um, uh, amine interactions, amines that are simpler than the ones we use commercially, but are now within reach because of this new technique, which is actually we refer to it as SQD. Um, and so that kind of gives you a snapshot of the state of the art. As of right now, today, we can't do the full commercial one yet, but we are, as I said, starting to get very close. And so with new research, we may be able to start having some kind of impact on that. Similarly, with molecular simulation, just in October, um, uh, this work came out by Cleveland Clinic, Michigan State, and IBM Quantum. And while they are primarily interested in new pharmaceuticals, so they're looking at drug discovery, they actually did a simulation of a methane dimmer. And what this is, it's the interaction between multiple hydrocarbons. And to me, this is very interesting because back in 2018, we were talking about hypothetically, how big would a quantum computer have to be to actually simulate hydrocarbons? And now it's finally happened. So this kind of gives you a snapshot in terms of the molecular simulation capabilities. We're doing simple hydrocarbons. We're starting to look at the simple amines. Um, and we've got techniques that are um, really leveraging not just quantum computing, but a combination of quantum computing and HPC. Quantum computing also does optimization. And in general, any quantum problem that we're solving, any of these molecular simulations, are a quantum optimization. And as it turns out, you can map um, any or almost any classical optimization to a quantum optimization. So for quite a number of years, we've known we can do optimization on quantum computers, but we haven't had a deep theoretical proof that quantum computers will outperform classical on optimization. And optimization tends to be on heuristics, tends to be very large data sets. But what we're starting to find out is um, we are seeing places where quantum computing algorithms scale better than classical algorithms. And what this means is that classical is outperforming quantum today, but as the quantum computers get bigger, the quantum computers should be able to outperform the classical. And so we did some work with Woodside, and it may sound like a not very exciting in terms of, gee whiz molecular stuff, but it turns out there's a massive cost, across a lot of industries of maintenance. And in oil and gas, there's only a 35% utilization rate. And so if you can schedule your workers in a more efficient fashion, then there's a potential massive money saving. And so with the work we did with Woodside, what we were trying to do is you want to avoid just sending your most senior, most qualified worker who can do everything to every site. Um, and you need to balance out um, your more junior workers and your less experienced workers. Otherwise, they're just sitting around, hence the low utilization rate. And so what we were able to show here, just to kind of give you a snapshot, we cannot outperform classical, but we can scale better, which basically means that as the size of the problem gets larger and larger, we will hit a point where classical will no longer be able to handle the problem, and quantum plus classical should be able to do it. Now, these are some older pieces of work, but just to show you, there's a broad range of use cases we've been looking at. With BP, we were modeling hydrogen, and it was one of the early combinations of machine learning and quantum computing, where we used a quantum computer to create training data for a large neural network, which allowed us to scale up from a very small molecular system to a much larger one. And so these are early steps towards understanding green hydrogen or even hydrogen combustion in internal engines. Work we did with Woodside a few years ago, we looked at how do you deal with streaming data when you're trying to optimize your LNG production. And then, as I mentioned earlier, work we had done with Eon was commodity price risk and hedging. The actual problem was, like a lot of utilities, Eon has to set a fixed price for the gas it sells to customers. They have to agree with uh, um, the government on what that price is. Normally, the way they do that is they look at all possible weather situations and say, Here's what the average is." And that's a very complicated or a very time-consuming and expensive process. And they found a method that would actually scale once we have better computers, and that could potentially outperform. So what makes for a good quantum computing use case for business? So first you're going to need data, and there's any type of enterprise data sets. You're really going to want to start focusing on problems that you can define with a small amount of data, or you can use HPC to kind of winnow your data down to a smaller amount because data entry on quantum computers is still a challenge. Then you want to focus on things like AI optimization or simulation. And perhaps further down the road, we will look at some physics-based um, uh, things. We down the road, we're looking at PDs. We might be able to do flow simulation for reservoir simulation or design of turbines, but that is a the research in that is much less mature. How do you do it and how do you get involved? So one of the first things is IBM has the most frequently used software Qiskit for programming on all systems. And so these numbers are actually a little bit old. There's a newer survey out, um, but the majority of quantum programmers prefer Qiskit. It's layered within our system um, to optimize performance. One of the latest things that just came out was announced earlier this week. Qiskit is 70 times faster than the next nearest competitor. Um, but this is an open source piece of software, essentially a piece of Python code. And so anybody who can program can start with this and have a very performant, easy to understand system that will get them running a quantum computer very quickly. And Qiskit is, at the very base level, we have our quantum computers and our high performance classical. Um, we have an orchestration layer that really makes the connection between the Qiskit and the hardware. We call it Qiskit serverless, plus Qiskit and HPC integration. So we're really just trying to make this, an entirely frictionless setup. On top of that, we have um, the Qiskit SDK transpiler service, um, and we are now building within the ecosystem. Some of our partners have developed functions. So essentially, if there's a problem that's been solved by somebody else that's very similar to you, you can actually buy their solution and implement it into your programming. Um, Over on the other side, Qiskit Code Assistant, we're basically using AI to help you code. We have a deep learning platform because nobody starts as a quantum computing expert. Um, and if you go to IBM Quantum, you will see there's courses, tutorials, educational materials, code snippets. There's a large range of things. It's probably the best place to start learning about quantum computing. Um, Another alternative, if you're not going to be doing it all yourself, is my team offers something we call the IBM Quantum Accelerator. If you don't necessarily have a quantum team in place, or you do have a quantum team, but they are loaded up with all of their other responsibilities, we can work with you. We look at year-long engagements where we help you map out a pipeline of use cases so you can develop a quantum strategy. And then we will build a prototype and we can do all the technical heavy lifting to demonstrate the validity of at least one of the use cases, and then put it actually deploy it on the state-of-the-art quantum systems that we have on our fleet, which is currently the largest fleet of quantum devices in the world. So I think to summarize that, we have worked with a lot of people in oil and gas, energy, and sustainability. Quantum is not yet a solution, but we are scratching the surface of the point where quantum may start outperforming classical in the next few years. We see incredible leaps forward in the hardware capability every year, but especially by 2029. And we would really like to create the future of quantum computing together with everyone because we very much understand we don't know all the problems. We build computers, we develop algorithms, and we'd like to work with uh, partners to advance not just technology but business. Thank you.
Thank you, Bob, for that wonderful talk. And we're excited to get to your questions here in a minute. Before we do, just a note on what you can find at these links that may be useful to you. The top right link is a link to our Quantum Business Foundations course, which, if you'd like to extend your exploration of quantum computing for enterprise, you can do so at this course that's available on IBM Quantum Learning, which is perfect for business leaders looking to understand and have meaningful conversations about the impact quantum may have on their organization and industry. And the bottom is the link to IBM Quantum Platform, where you can get started programming quantum computers from your laptop, our enterprise grade utility scale quantum computers. So feel free to check those out, and we will get to your questions here. So a number of great questions. First, Bob, we have a question. How do you evaluate the role of quantum computing in accelerating the transition to renewable energy sources, especially in the dynamic management of electricity grids?
That's a great question. Kind of the state of the art of quantum computing is we're looking at use cases. So modernizing the whole grid is a very big problem, and so we're trying to pick out pieces of it. So I see potential in finding ways to more quickly optimize changes in the grid. I see quantum computing playing a role in determining how to invest when you're expanding the grid. And I also see quantum computing playing a role in uh, actually modeling the physics of the grid. So there's a number of different places we do where we struggle perhaps a bit is that these are fairly large optimization problems. So we're on the path to solving them.
Great, thank you. Okay, let's see. All right, so looking at the potential applications, it seems like the majority of your customers are energy producers, power plants, battery manufacturers, grid providers, etc. But what would you recommend as a use case for a large company that is not actively in the energy market, but would like to optimize its usage, become more sustainable, and develop new revenue streams?
Yes, that's an interesting question. So, I mean, this webinar is focused on those particular sectors, but we work across all the other sectors, so there may be other use cases. Um, if I'm understanding the question correctly, you are a different industry, but you use energy and you want to optimize your energy use. You can explore things like what are the what is the optimal load, that we're using and when are we using it so that we are focused on more green energies? Is there a mix of sources that you could use? Is it really just a timing thing so that you're not using the grid at the top at the, peak hours? Um, so those are some of the things I can think of, optimizing your use. But as I said, there are applications across pretty much every industry out there. And so there may be other applications independent of energy where quantum computing could be helpful.
Great. All right, so how do you evaluate the current appetite in the oil and gas, chemicals, mining, and utilities execs for quantum computing?
Um, I've spent a lot of time in oil and gas, and some of these other industries. Um, the appetite for technology generally varies a lot from company to company. It's always been a little amazing to me how different people do exactly the same job. So there are certain companies who are very tech first. They want to be the leading edge. They're looking at, how quantum and digital technology in general gives them opportunities to create new products, to optimize, uh, their current revenue streams. And then, to be really honest, there's a lot of companies who are um, thin margin. They're looking at the next quarter. And so those companies are going to be later adopters. So what I would say is the leading companies are very interested at the top levels, but there's a lot of companies that are just, when this is a commodity and it's going to come off of a shelf, I'll buy it off the shelf.
Great. So we have a question in the chat about our continuous path from error mitigation to error correction, and people are wondering, what's going to really happen between 2028 and 2029 that's going to switch from error mitigation to true error correction, boosting the gates so dramatically.
Yes. So on that chart is what's going to be available publicly. Behind the scenes, there's a more continuous improvement. But the biggest change is actually going to be in the hardware with couplers. And so one of the ways to really improve error correction is to make connections uh, across chips and then between chips, make quantum connections. And it turns out that if you have a certain distance between the things you're connecting, you can really reduce the amount of resources you need to do the error correction. So it was last year. I think last September, a paper came out that said we figured out theoretically how to do this, but it's really a change in the hardware. So there's these connections have to be built and put on the system.
Okay, let's see. We have another question on, yes, so how do you address the current challenges in terms of scalability and noise in quantum hardware?
Um, we have some of the finest, hardest working people around worrying about that every single day. So that is not one single problem. It's every aspect of it. So people are worried about qubit fidelity, qubit stability, gate fidelity, network setup, error mitigation, error correction. So, and then scalability, because every time you make something bigger, it introduces new problems you thought you had already solved. So it's a massive engineering challenge, and we've been very successful at hitting the goals we set out. So one of the things about it is we're not just throwing numbers up in the air. We actually have a path to how we're going to achieve all of those goals.
Great. Okay, let's see. Do we have any others? I think one on what you think of quantum computing enhanced reservoir simulation, and we'll conclude with that one so that we can move to the final survey. So, yes,
Uh,
quantum computing enhanced reservoir simulation.
Um, so this is a topic very close to my heart as I've done decades of reservoir simulation. Um, so on the conservative side, we are a ways off from being able to do the kind of partial differential equations that are the flow equation. We'll probably see some things where we can do some of the chemical reactions between hydrocarbons and the rock surface that we're not able to do now. On the aspirational side, there was actually work done by Toyota on our systems where they had a finite element model. And what they were really trying to do, the problem with simulation is you don't just need one simulation, you need to run a number of them and find the best one. And so I think the aspirational goal is to simultaneously do multiple simulations so you find the best one in the first run that you do. So, yes, it's early days for a lot of these pieces, but the goal is something where you can very quickly find the best simulation.
Thank you.